All right, so welcome back for the very last talk of today's blockchain meetup, for the very last talk of the very first blockchain meetup in Brno. And I'm happy to introduce you Mališa.
Yeah, thanks.
From Serbia, who will tell you a bit more about the three most important blockchain-based apps.
Yeah, something like that.
So please give warm welcome to Mališa.
I should have figured.
And one more note, please turn off the Wi-Fi because we've got some difficulties with internet. So anyone using internet, please turn off the Wi-Fi. Thank you.
Thanks. Great to be here. I'll try to be as brief as I can be. Okay, because we are tired. It's past my bedtime.
Excuse me.
Yeah.
To move there.
Here?
Thank you.
Okay, great. So, I'm not sure are those three, let's call, how did I call them in English? Three blockchain-related architecture, the most important ones, but those are the three I recognized and I didn't read somewhere else. So I'll talk about them. And we will have two case studies. One is about email decentralized app, you see? And the other thing is about lending and borrowing on blockchain. And those two have different architectures. So the first one, before we start with the first one, which I called on-chain architecture. On-chain and off-chain are new terms. Like on-chain is something that happens on blockchain, and off-chain is something that happens outside of the blockchain. Yeah. Before we start, how many of you have done something with Ethereum? Do you know what is Ethereum? Ethereum, yeah, okay, so I'll talk for 3 minutes about Ethereum. So you now know about blockchain and Bitcoin, okay? So one guy, that famous Vitalik Buterin, said, okay, let's do something different on blockchain. Let's do everything on blockchain. Not just financial things, but all the things in the world. So we all know what is a Turing complete system. Computers, yeah. So let's do a Turing complete blockchain system. So let's introduce smart contracts. Smart contract is basically a class or a library or whatever, in which you can program something that is Turing complete and which can do anything, have inputs, have outputs, and meets events. And the final thing is a transaction, which Book explained a little bit 5 minutes ago. So let's do any decentralized app in the world on top of blockchain. How good is that? Do you follow me? How good is that? Yeah. So you do everything. You have a front end and you have no back end. You have a blockchain as a back end. Okay, that is revolutionary. So basically, this is how on-chain architecture is basically how people think of when they find out something about Ethereum. This is how they think it works. And it can work like that. But basically, business logic is done on the blockchain and business logic inside of the smart. So I'm talking about the first, I'm not talking about Ethereum now, I'm talking about on-chain architecture that can be implemented on top of Ethereum or any other kind of blockchain that has something like a Turing complete system, something like a Hyperledger or whatever. So in this kind of architecture, you put business logic on blockchain. You can do this by using smart contracts. Yeah, okay, great. But not only that, you put all user-generated data on the blockchain. So basically, when something user sends to a business logic, you put it on a blockchain in the transaction. Okay. So I see rolling eyes. I see how this happens. Okay. So we will. I think we can introduce something called decentralized application, which is when you say a dApp, you see there a dApp with upper D and upper A, then you mean Ethereum. Okay. So dApp, in a most broad sense, it's a front end plus contracts. So you read this. it functions differently than a client-server architecture because you don't have a server, you have a blockchain. You have some smart contract which you call, and you give him input, and you get some output that is a transaction, which you know that will be there on a blockchain, and nobody can tamper with it. Nobody can delete your data or whatever, but your data is public. So for what use case is this good? Okay. Elections. Okay. On-chain architecture is, for example, good for decentralized applications for elections. So you have, this is from Google. I like the image. So on the left, upper left, you have a country that holds an election. Yeah. So basically, before we start, what is the wrong with, for example, I'm not familiar. Do you have elections on? Do you have a paper or do you? Yeah. Yeah, I do in my country too. So basically, the reason why we don't have, I guess, besides we are lazy, but besides that, basically the reason why we don't have that, who will be authority that will say we trust this server to be a bulletproof system that hacker cannot go into, or some corrupted government or whatever. So those are the reasons why we have a problem with not only that, but those are additional reasons why we have a problem. So the way we could solve this is by using some kind of blockchain, for example, Ethereum, which have a smart contract. So this country deploys a decentralized application. The country creates a smart contract. It creates all the users in the country get some public-private key pair. I'm not sure where in the ID or whatever. Okay. And the country says to the people, okay, now go to vote. So a DAO. DAO is a decentralized, it's a broader thing than a decentralized application. It's decentralized autonomous organization. Why autonomous? Because once deployed to the blockchain, this application is autonomous because nobody can delete it and all the stuff with the transaction. And this is decentralized because of the consensus and the miners and whatever. On the side note, Ethereum also functions currently on a proof of work mining. So the country or whatever deploys the organization on a blockchain. So it has some rules, smart contract rules. And those are the conditions, the third step. This is ensured by embedding predefined conditions into code. So you have to code function vote, function sum up all the votes, add new people for the into voting system or whatever. You know? The same functionality as you do have in the central systems, you have them in the decentralized system. So the fourth step is voting tokens are issued, so you get some private public key pair that is connected to your vote or whatever. And you vote, and every vote is recorded and processed on the Ethereum blockchain, which ensures transparency and decentralization. Why transparency? Because every vote is one transaction, yeah? So anybody, each one of us can go to some decentralized app, log into, and see on the public Ethereum blockchain or whatever blockchain, not who voted for which person, but the sum of all votes. And each transaction is recorded. This private key. So anonymity is an issue, so I'll not go into that. But basically, this on-chain architecture is good for applications like that. Any questions for now? Do you have any idea how this functions in reality? Yeah, great.
Is the contract always public so the voters could inspect it?
Yeah, I'll show you a contract. Best way to imagine is to see. So this is what. Do we have something like, okay. In the case of, you using breed. It's a blog. Okay, let's move on until this loads up. So basically, I wanted to show you.
It will never load up.
It will never load. So basically, smart contract is totally public and anybody can see it. You deploy it on a blockchain. So let's try again. And I can, so imagine that the internet works, so I go into a smart contract and I see all the functions. And this is, let me show you. Sorry. Sorry. So I will move back to the slide. So this is the question. Code is public, the last one. This is a pro. It's a good thing because everybody can see the code. But also it's a bad thing. On the left, it's a con because anybody can see the code and call it. Anybody can call your code. Anybody can call your function. So everybody sees all of your functionalities, and anybody on the network can call all of your functionalities. Okay? And try to call them. So for example, I have a functionality which I want only the owner of the smart contract can call. But something goes wrong, and I didn't define very well the functionality, so everybody can see it. So like 10 days ago, there was a multi-sig wallet which was hacked because it wasn't initialized properly. So the guy called like, I'm the owner of the contract, and then the guy killed after that the contract. So a couple of 100 millions are stuck, for example. So the good thing about these apps are the code is public, and anybody can try to execute it. But at the same time, it's bad. Okay. The pro is temper resistance. So basically, once we vote, this cannot be deleted, edited, or whatever. Or total trust in the data. Nobody can corrupt. So my lecture is good because the book was before me. So we know now why we cannot totally trust the data. The good thing is code is law. So once you code something, it's the law. So for example, if I didn't code into my contract that I can get my money back, I cannot get my money back. So this is also a pro and con. Those are the upsides. Okay, code is law. So you know there is a famous saying in Google, "Don't be evil," and those guys who invented code is law said, "Can't be evil because code is law." Cons, performance and speed. 10-minute blocks. Performance and speed. Nobody wants to wait for 10 minutes for anything, you know. Unknown engineering path, but because I think this is so obvious, because plenty of people said like, no backend. What? Unknown engineering path. So this is the road less traveled, so you have to learn a lot and to see what's good and what's bad. So I'll take you for the questions about that. I want to talk more about those second two architectures. Ever-changing cost of operations. Okay, does anybody have an idea what is this? So when I have an AWS server, I pay Amazon $10,000, $100,000, whatever, and I can have the calculator more or less. I don't like their calculator. So basically, I can say like $100 I can manage, and I know that, for example, $100 is this month, next month, and if I raise more customers, and it will grow, but I can manage that because it depends on the Amazon and me. So we decide what's the price. But on blockchain, this is different. So Nicola said about gas. So basically, most trivially, what is a guess? Because this smart contract can execute anything in the world, okay? How do you know when to stop? So I can code into contract for infinity do this, while true some I plus whatever. So how does the blockchain or miners know to kill my functionality? They don't. So what is the first idea that comes up to my mind? How to kill the function in order not to have an infinite loop? Well, first is like timeout, 10 seconds. But you know, miners or nodes can have different powers. Computers are with different CPUs, GPUs, or whatever. So on my laptop and on your miner, 10 seconds are not the same. Yeah, so you can do a lot more on your laptop or on your supercomputer than me. So we have to have some discrete thing, and that is a guess. So amount of gas you're willing to provide to anybody in the network who is willing to execute your functionality is the discrete thing which you provide to the network. Gas is, imagine a gas that is related to some coin, which is Ether or most trivially Bitcoin. It doesn't have anything with Bitcoin, but Ether is something in this blockchain that is same as Bitcoin in Bitcoin blockchain. And gas has some proportional, some relation to the Ether, okay? So you have to pay the gas in order to execute your functions. That's it. So some gas cost for any function. So, sorry. This is from 2 days ago, Excel sheet, which shows you how on the left there are functionalities. For example, sum of two integers, sum, for example, compare two integers 1 million times. And on that day, gas required for that action was 3 million. And when you translate that to dollars, that is $26. Okay? $26 for comparing two integers 1 million times. I'm not sure. Is that? It's not cheap. So, but this is more demonstrative. Like, save 1 gigabyte storage to a blockchain costs $5 million. Okay, now we left. Or save 1 megabyte on the Ethereum blockchain costs $5,000 2 days ago. So you don't want to save the data on blockchain. But we said on-chain architecture. All user-generated data is stored in the blockchain. In this architecture, we have to store the votes on the blockchain. So this is good for voting because there are like 6 million people, 10 million people, 10 million transactions, whatever. We can pay that cost. But for large sums, do we hear each other? Yeah? But for large sums of functionalities or daily usage, this is not good. So that's why, for example, voting is good for this pattern. Let's move back. Ever-changing cost of operation. So we said that this, say, 1 gigabyte of storage is 5 million. That doesn't mean that tomorrow it will not be 10 million or $2 or $3 because it depends on the price of Ether. So you tied the economy of a blockchain to the currency you have. And that is good and that is bad. I don't want to go into details, but this is important for you to know if you want to play around with Ether or any other, let's call it utility or protocol token for creating a decentralized or whatever kind of application because of those protocol economy. You have to pay the fee. On Amazon, or Azure or whatever, it's pretty simple. You paid dollars in some linear manner or whatever. But here, it changes and it reflects the volatility of the market. So today you pay for 1 megabyte 5,000, tomorrow 10,000, and the day after that $1. I'm joking. So now we know the pros and cons, and we maybe know something about the first architecture that somebody can think of when he reads the word Ethereum. So the second one, okay, this data is too expensive, so we have to use smart contracts, okay, we have to trust the network or whatever. So we will still have a business logic inside of the smart contracts, yeah? But we will have some, this is the middleware logic, will be the consequence of user-generated data is not stored on the blockchain, but on some other network, and blockchain stores only the metadata. So you say, okay, this is too expensive to store 1 megabyte, 2 megabytes, or whatever on blockchain. This is crazy. So what I'll do, I'll move the data somewhere else. I have the hash or URL of that, and I will put URL into blockchain. Okay, but the consequence of that is you now have two networks, blockchain and whatever network keeps the data. Who is connecting that? Who is the guy? The client. In this pattern, which we called client king architecture, I made up the name because the client is the king. Okay. The client is the middleware. It has middleware logic. So it connects the blockchain and data storage or whatever. So this is, for example, not known path. It is a pattern, famous pattern called client king pattern. Okay, so the way it works is, this is a front end. It can be a mobile app. It cannot be because I don't want to go into it. The state is not ready for the mobile app on a blockchain, not in a decentralized way anyway. But it can be a Chrome or some app on the computer. And this front end has a connection with the blockchain and some other, in this case, peer-to-peer data storage. You have heard about IPFS. IPFS is Interplanetary File System, and those guys are great. They have a Filecoin, and they have a lot of things. They aim to replace HTTP, so look out. IPFS is pretty good for streaming and storing the data and blah, blah, blah. It's a peer-to-peer network. It has a lot of similarities with blockchain, but it's totally different. So basically, imagine it as a black box to which you put, it's a peer-to-peer system, like a torrent or whatever, you put your file there, and you get back some hash, which uniquely identifies your file on the system, yeah? So what you do is, a user adds a file or whatever. So you put file there, step one, you get back the hash, you have the hash, then you put the transaction with the hash on Ethereum, and you get back, okay, great. So once the user comes back, this is a metadata. So once the user, for example, comes back, what you do is you collect all transactions connected with that user back, you get the metadata, and then you go to IPFS and collect the data. So business logic is here and here. Middleware is front end. So this application is a big application, this front-end application. So it's imagine it as those old applications which have everything in it, like a Microsoft Word. So, joking. So yeah, so this is a use case of what we have built, my team and I. A centralized email service, Lemon. and it's basically serverless email. So the way it functions is this. You write subject, body, add a file, or whatever. We encrypt that with your private key and the public key of the recipient. We put all of that onto IPFS. We get the hash back, and we put the transaction on Ethereum. So the guy who wants an email will receive a notification from Ethereum. Hey, you got a transaction. So he has okay, have a metadata, go to IPFS. I got an email. It's an email. So we have a gateway for Gmail or whatever. So I don't want to go into details, but I wanted to show you when it's good to have a client architecture. It's good for example, personal applications, but I don't want to go far ahead because I have a conclusion. Pros and cons. Pro is cheaper. This table does not exist here. So basically, you don't store 1 megabyte. You have some metadata that is nearly irrelevant. So still, you have a total trust in the product. So because you can have a checksum on Ether or whatever, you still have some nearly total trust in the system. Also, you have a smart contract, so code execution is public. That is good and that is bad. Data can be lost. Okay, so no, this is a con. I don't know why I put it to pro. Maybe it's a pro, I don't know. Yeah, it can be a pro because, you know, on the blockchain data cannot be lost. That's sometimes bad. So, yeah, what I wanted to say is total trust. Okay, so cons. Complicated client side. Okay, I think this is a con. Nobody wants to have a complicated client side because of the second one, backward compatibility. So imagine you have deployed a new contract. You're not very pleased with your old contract. So now you have a hell with upgrading application on the client side. So continuous delivery and deployment are not good. Search complexity. Yeah, I missed that in the first case. Search complexity here and search complexity here. So, okay, we have the data on a blockchain. How to search it? No way. There's no way. Here, you don't even have a, here, you don't have a server, yeah? Here you have a client. So on a client king architecture, you can search things on a client. That means that fetch me every information about me and I'll search it in the front end. This is crazy. So I think nobody does it. So in the on-chain architecture, the smart contract can do that. But remember the cost of operation. So when you load up 1 million things, it will cost you money. So you don't want to search something in a blockchain if it is not something that is more relevant to you than the money you will spend. So if you search an email that is totally irrelevant and you pay $50, $100 for it, then you will not search it, you know? Okay. But if you search for 30, how did you say, Nicola? 3,000 bitcoins, you will pay like $50, $100 or whatever. So it depends on the, not only on the, it depends on the price you put in into a transaction. The thing is that basically the transactions that are low cost, okay, and high frequency, not very good for blockchains and Ethereum because For example, email. How would you put the price on an email? Is it 1 cent? Is it 30 cents? Is it how much the one email costs? But in the case if you send money via email, which is a possibility on a blockchain, I have an attachment in email, I send you 20 ethers, then this transaction is more relevant to me. So I don't want to go into details, but search complexity, basically the only way I know now how this function is that you have a big server which listens to all the transactions, index them somewhere in Elasticsearch or whatever, so you search the central system. Okay. There is no easy way to search the blockchain because it was not made for search. So you have to load, remember, blocks. So you have to load all the blocks, then you have to open them, then you have to pull out the transactions, then you have to see what transactions you want, blah, blah, blah. So it's not so easy to search. So the complexity is big. So when somebody comes with an idea, I want to build a decentralized Facebook. And people all the day have those ideas. I want to have a decentralized application that is Facebook. Okay, then ask them, how will you do the search? And they will go away. So, yeah, so basically, there is no easy way to do the search. You have to have some central servers or whatever. So this is a big, big con. So this is extended client king architecture 2.1. Did you hear about Blockstack? So Blockstack is I really like this project. So it's an adaptive, it's a hybrid model. They didn't know that it's a client king, you know, but but I know. So basically, they have a lot. I don't want to check out. They build the decentralized internet, the new big thing or whatever. But I want to go into a technical solution they provide. So this layer is a blockchain layer. And in their case, currently it's a Bitcoin. And this is what they keep here. They load up. I will go into it. They load up all the transactions that are like tagged, that are important to them. This local DB. They index that, and then they can know some things. And the things they know are these. So basically, domain name, public key, and zone file hash. So by knowing these three things are basically put in every transaction that is relevant to them. So they tag on a Bitcoin. In Bitcoin, you can color a transaction or whatever. So you can tag it, and you have some additional data inside of transactions. So these are additional data for those transactions they have. Domain name, public key, and zone file hash. So let's say by knowing a public key, they know who is the owner of domain. So I can prove that I'm the real owner of some domain. So I say, for example, my name is Mališa, so I say mališa.id, okay, is my domain name. And I place a public key, and I say zone file hash. I hash my zone file, and I will say what is a zone file, basically, you know. And I put those three informations in the blockchain. So everybody who bootstraps the system will load up that and can check that I'm the real owner of that domain, and that zone file hash is the real thing by hashing the zone file. And zone file has, and this is a zone file, zone file has information where is my real data, not metadata, like my picture, my bio, my whatever, my Facebook ID or whatever is stored. So I say, my zone file is on Dropbox, and they can check by knowing zone file hash, is it really true? So they have a big client, and they have a system, fat client, client king, so they can load up all from blockchain, and it's an initial bootstrap proof of identity thing, which creates a decentralized internet, yeah? Because I don't need to trust you that you will tell me that your idea is there or whatever, I can see on the blockchain where it really is and what internet says about you. Check it out. This is a brief example of a client king, and it's called Blockstack. So if you have a question now or later or whatever. The third one. So oracles. So basically, because these blockchains are walled gardens, are like isolated networks of things, and they cannot easily interact with the rest of the world. Basically, they cannot interact with the rest of the world in any way. So they have to call somebody, provide me with information, what is the weather in Brno, like how much degrees are in Brno. So the smart contracts call somebody, some server or whatever, basically it emits events. So I'm interested in this, okay. So there are subscribers, they call, so they have the weather information and they call the contract like, this is the weather information. What's the problem with this? Does anybody have an idea? Total trust in the product. So maybe this server lied. Maybe it said it's 30 degrees and it's 28. So, you know, how to trust that server. I can trust your smart contract, but how this smart contract maybe is totally honest. It cannot lie, and code is law. But this third-party server lies about whatever, market state, okay? So how to trust it? So we introduce oracles. Trust me, I'm an oracle, okay? So this is the term, like the trusted parties in whichever way. I don't want to go into details. For example, Microsoft Azure has, how do you call them, cryptlets. It's a hardware-based system. I don't want to go into details, but the idea is Oracle is not something that guarantees that the rest of the internet is not lying to you. It is guaranteeing that itself is not lying to you. You know? I'm not lying to you. Maybe this guy is lying to you, but I am not lying to you. So this is Oracle, okay? So basically, you can trust it. So the one step further is, I'm not lying to you, and this guy is not lying to you. Okay. So basically, now you can build some internet around it, some real apps. Now you are not only isolated in a walled garden. Now you can communicate with the rest of the world. So you have read this. I can go. This is an example. Okay. So I have an application about lending and borrowing money. Yeah. So I want to lend and you want to borrow, or vice versa. I want to borrow, you want to lend. So I want to borrow 1,000 bitcoins, 1,000 ethers, $1,000, whatever. So yeah, give me. I'm joking. So basically, and you are willing to lend me that money. Okay. So what happens if I go to Australia and disappear? Okay. On Ethereum, you cannot do anything from me. You sent me 1,000 ethers. Go and complain to blockchain. Okay? So, yeah. So basically, what you can do is you can notify, the smart contract can try this. Okay, guy, you signed the contract to give the money back, and this is me. And he says, give me money. I said, there's no response. And this is a voucher. Hey, you said that you will, instead of these guys, give me money. Oh, I will not give you money. So this smart contract emits event. These guys are not giving me money. Okay? And this is an oracle. Hey, off-chain service, police, go and arrest those people. This is an off-chain service. Okay? And I arrested them. Oh, I will arrest them, whatever. Yeah. This is a number 5. And Oracle says, the thing is solved. Okay, so so the 6th one is, okay, change the state, whatever. Smart contract, change the state. I reacted, so do whatever you want. So the way it works is these oracles provide you with enough services, those are services, whatever, providers, with enough, yeah, credibility, like you cannot, with on-chain, this is the third one, so on-chain architecture and client-king architecture, we have a problem with the real-life things. So it's good to have an email or whatever, but if you want to do something like lending and borrowing, then this is a better use case to have Oracle's architecture. So let me give you an example about lending and borrowing in a, how do you think in a Oracle's architecture way? Let's say it like that. So in a software as a service manner, you would do this. You will have a fat server with all the business logic. And you have to log into the server, and then you have to say I'm a lender or I'm a borrower. Then you have to say to the server, I'm willing to lend this amount, and these guys, I'm willing to borrow this amount, and this server is knowing all of that in that distributed central database. And then whatever, you match them in the server and notify them, and it's a middleman, okay? And this is the blockchain is trying to solve. So, aka decentralization. So you don't want to have some smart contract that will know, that will be some kind of central server in some kind of way. So you want to build a peer-to-peer system. So you have a peer that is borrower, you have a peer that is lender, you have a peer that is voucher, you have a peer that is matcher, you have a peer that is Celsius Oracle, or Oracle, whatever, off-chain provider, and smart contract. So what smart contract is just one thing in Oracle's architecture. So how this functions? And remember, this is not a server. This is a peer, and this is a peer, and all peers are equal. But this peer has a different functionality than this peer, and with this peer, and with this peer. So the functionality of the matcher is basically, I call up the matcher, which is peer, and say, I'm willing to borrow 1,000 ethers. And this guy is, I'm willing to lend 1,000 ethers. So this peer, big peer, is saying to, and you can have matchers, like thousands of matchers or whatever. I'm saying this, I'm interested in this match or whatever. So they match. And then this is a matching. So I'm willing to lend, oh, okay. And this, so when this lender and this borrower have enough information about each other, borrower calls up the lender in a peer-to-peer manner, not via server. Hey guy, give me money. Okay, here's your money. Or this is not, okay, here's your money. Okay, I have signed your request. And you can go to the smart contract with this, my signature. So, hey, this guy signed the request. So this smart contract says, okay, I checked it via private public key. Okay, it's good enough. Smart contract calls this guy. Give me money. Okay, here's the money. Here's the money. Okay. And then, if something goes wrong, you introduce a peer called Oracle, which listens to all the events in the network that are emitted on smart contracts. For example, when this guy calls up, this smart contract can emit event. Hey, new contract, or hey, new lending proposal, whatever. So Celsius, Celsius. Oracle can know about it. Okay? Any questions for now? No. Okay, so pros and cons. So basically, an Oracle architecture is all about building a big peer-to-peer system. Not only with smart contract and client or whatever, but with plenty of different peers. And I'll introduce, besides of Ethereum, that is a blockchain, there is a Whisper system, which is developed by Ethereum community, And Whisper system is a peer-to-peer communication platform. So those arrows between borrower and lender can be in implementation or detail implemented on top of that Whisper. Okay, just an example. So pros and cons, performance, yeah? Because you have decentralized or distributed business logic and middleware logic and data to various peers. Also, you can use existing technologies like AWS. So this matcher, even though it is a peer, it doesn't mean that it cannot run on AWS and be a distributed big thing that is very, very smart. So you have a competitive matchers. So my matcher is better than your matchers. Easily upgradable because you have a central parts. You can easily upgrade them because they're in total control. You have control over them. You can do anything that any software as a service can, even search. And matcher is a proof. You can search the data. You can match persons, yeah? Because you have a central database, even though you have a blockchain. Cons, trust issues. You have a central database. So you're an evil person because you have a central database. And decentralization is harder to achieve because you have a central database or a central server. You cannot say that you are a decentralized thing, even though you have peers. People will say, but you have a central MySQL, fuck you. Sorry. That happens to me every day. So how to pick the right architecture? If you need it now, and for the masses, pick the Oracle system or go centralized, or go AWS. Don't use on-chain architecture if people use the product for non-fintech stuff. Okay, so don't use it for building a new Facebook. I recognize Client King as a totally architecture for personal labs. So, for example, taking notes and stuff like that, Client King. If you just promise things, say total decentralization. People like it. So this leads me to the last slide. So if you just promise things, go with total decentralization. So there are two basic types of blockchain projects. Ones that say we will have an ICO, and ones they say we will not have an ICO. So once they say we will have an ICO, they will say we will have a decentralized ICO, basically. And once they say we will not have an ICO, they will have it, but in a different way. So, thanks.
All right. Any questions? So if not now, we can stay here till 11 o'clock. So 1 more hour to walk around the nuclear shelter and get more boost. Feel free to stay here. Feel free to talk to our speakers. And thank you all for coming for the very first blockchain meetup. And hope to see you next time. Thanks.